Okay, so up to this point, we've learned what it means for a sequence to converge, and we've introduced two properties, boundedness and monotonicity, that can help us determine if a given sequence converges. And so at this point, we're ready to consider that second question that was posed in the last video, which is, if we know a sequence converges, how do we determine what it converges to? And so in these next two videos, we're going to present a bunch of rules that address that particular question. And the first set of methods we're going to introduce, we could just think of as rules. I'm going to go ahead and prove some of these, but it'll be an optional video for you to view. Some of these rules you probably already know, or they make sense. For example, case number 4 definitely is something that makes sense to most people. Cases 2 and 3, where we're dealing with the nth root, may or may not be so obvious. Case 6 is a very famous limit. It basically tells us how we can get e to the x. And we're going to use this later on when we study probability theory. And so on the one hand, we could remember these rules, but one thing that will help you remember them, and it's useful to know in general, is that these rules reflect a certain hierarchy in how fast functions grow. And let me show you how this hierarchy goes. It says that the natural log does not grow as fast as powers, which do not grow as fast as exponents, which do not grow as fast as exponentials, which do not grow as fast as n to the n. Okay, and so if you understand this hierarchy, what this means is, this means that if I take any one of these that's less than the other, look at their ratio and take the limit, it's 0. That's what it means to grow less fast. So for example, if I took the limit as n goes to infinity of the natural log of n over n squared, this goes to 0. This is what this hierarchy says. Okay, why? Because the natural log of n does not grow as fast as n to the p power. And of course, there's some qualifications here. You know, you should recognize that p is greater than 0, and also in the exponents, b is greater than 0 too. Okay? But if you know this hierarchy, it's very useful in general. It will definitely help you remember a couple of these rules. Okay, the next thing we want to do is we want to take over our knowledge of limits that we learned before. And basically, they're going to let us determine what the limit of convergent sequences are when we start to take linear combinations and start to do algebraic operations on them. So we're going to say that if we have some sequence a sub n that converges to alpha and some real sequence b sub n that converges to beta, then the sequence that's formed by the linear combination converges to what we think it should converge to. In other words, one way to think about this is that when we take the limit basically distributes across this sum. That's one way of thinking about it. It's useful noting that this general result contains some special cases. So for example, when d is equal to 0, we see that the sequence, when we multiply our known sequence by a scalar, is just that scalar times whatever that sequence converges to. And if we let c be equal to 1 and d be equal to -1, we see that this tells us about the difference of two convergent sequences. Okay? It also tells us about the product of convergent sequences, which is very useful. So for example, if I let an be the sequence 1 minus 1 over n, and I let bn be the sequence, we'll just make it 1 plus 1 over n. We know that these both converge to 1, so alpha is 1, beta is 1, and this result tells us then that the sequence formed by the product of these two sequences just converges to alpha times beta, which is going to be 1. Okay? We have a similar result for the quotient, okay, with these caveats that we can't have terms being 0. And a very useful result that we're going to actually prove in the next video is that if we take a convergent sequence and we raise all the terms to the same power, it converges to the limit of that sequence raised to the same power. So for example, if I know that the sequence 1 over n converges to 0, this automatically tells me that this sequence also converges to 0, 1 over the square root of n. Okay. So this is a nice justification for this. Okay, in the next video we're going to see some more general techniques that we can use to evaluate limits of sequences.